Right, so let's try number 19 and 12.5, which is, I fully acknowledge, an unfair question. Okay, so there's this function, f of x, y, and z, that's 2x minus 3y plus z minus 20, which gives you what? Like, I'm hoping that you guys think of functions like this.
Input, output?
Right, they're like an input and an output pair, kind of. Right? Like a function's just a rule. It takes inputs and makes them into outputs. And yeah, there's some restrictions on that, but really this is all there is. What are the inputs in here and what are the outputs? Like, they tell you something in the problem. What do they tell you?
We have x, y, and z. Don't have to put the output.
So it says, suppose the function f gives the temperature in degrees at a point. Right? So what's the category of input here?
Like affect temperature?
No.
Position.
Dumber. Go down a level. So this is literally taking a point, right? And it turns that point into a temperature. And yeah, there's probably a mess of factors affecting that, but literally the inputs are just points and the outputs are temperatures. It's cool with this? And this rule is named F. Great. Okay. When it asks me to describe isotherms, anybody know what an isotherm is?
The locations where the temperature is the same.
Yeah, that's a location where the temperature is the same, right? They probably told you that somewhere in the book. Also, you could Google this. So how do I find a spot where the temperatures are the same?
Where f, x, y, and z, the combination of x, y, and z still equal the same f value?
Yeah, you guys see this, right? If they're going to be the same temperature, right, that's an output thing. So I should take the output, f of x, y, and z, right, and set it equal to some damn thing, right? So I'm going to just set it equal to k. K standing for constant. So k is going to be 2x minus 3y plus z minus 20, right? What kind of object is this if k is a number? Yeah, this is a plane, right? We just learned that in the last section, which is good because really that's the only object I know right now anyway. You guys see that? So the isotherms are planes. Cool. All right, part B asks, and this is the one that's not fair, I think. Part B asks, calculate f with a little z and then 0, 0, 0, right? Okay, and Ryan's complaint was what?
Well, I'm seeing now that the f with a little z is probably something different than a regular f. I just plugged zeros in and got a negative 20.
Totally. Right? So if you didn't have the little z, right, you just do do f to 0, 0, 0, right? So what are you going to get?
Negative 20.
Negative 20. Great. What does that tell you? That tells you the origin, right? The spot you set up your coordinate system has what? Negative 20 degrees Fahrenheit for a temperature,
Darn cool.
which is cold.
At least it's not Celsius.
Yeah, it's not Celsius.
So are these isotherms like rectangular prism shaped, or?
No, these isotherms are planar.
Okay.
So they have no thickness, right? Because any deviation off by a little bit apparently changes the temperature a little bit. But they're stacked planes, right?
Okay, so what makes this different from like, because I saw in the book there was an equation of like different nested spheres.
Yep.
Which I think was just like, you know, x plus y plus z all squared, or?
Yep.
Yep. So that would be,
Ellipsoid.
so what I would think in terms of temperature, right, is if I have a Bunsen burner and I light it, right, the temperature is going to spread out in shallows, right? That's going to be that like nested spheres thing that you're thinking of.
Right, so this one isn't in 3 dimensions though, because why?
So the shapes are still, right, the surface of a sphere is still kind of a 2-dimensional object, right?
Okay.
So these are still kind of 2-dimensional sacks, but they're not wrapped around. So this is just leaves, right? Yes?
Yeah, like instead of a bunch of birds.
This would be this would be a lot like if you had a book, right, and you heated the bottom of the book, right? As the heat creeps through the pages, right, it's going to go down. You guys all see that?
Yeah.
So these planes aren't flat, right? They're kind of tipped, but who cares? They're just tipped planes. And so you have this world, right, where there's heat being applied in kind of from one plane, and it's just spreading out. You guys all see that? Okay. I still don't know what FC is.
It's a derivative of focusing on Z.
Yeah, so this is super not fair, but that's a Z derivative. So what is the rate of change in the Z direction? I mean, you guys can see though, right? Like, here's a function. What happens if you change Z a little bit? It goes up by a little bit, right? It goes up by 1 times whatever you change Z by.
So
Yeah.
if it was like 2, if they were looking for like partial derivative of x, it would be 2 then?
Perfect. Yeah, so the x coefficient's 2, the y coefficient's -3. Great. If they asked for FW, right, if they asked for what's F sub W,
0.
yeah, this would be identically 0 because there aren't any friggin' W's in that thing. Right? It's constant with respect to W. Does that kind of make sense?
Would that change the values?
Oh, no, in this case all the derivatives are constant because it's a plane, right? It's flat. You guys remember that one? I said, when we talked about planes initially, I said, well, they're flat, right? And there's this differential idea of what flat means. It just means that all the derivatives are constant.
Does that mean when you kind of find the f of z, unless there's like a 2xz or something like that, the x and y's are kind of negligible as to what they end up being for the derivative?
Yeah, exactly. When I calculate a z derivative, right, the x and y are constant with respect to z. So really, you could think to yourself, and this is wrong, I'm going to write something right now that I don't want you to put in your head, but you could think to yourself, hit this thing with a ddz, right, of f. And the only part of this that's wrong is that that's not the whole story, right?
Okay.
So I'm going to make new d's to tell you that that's not the whole story, and I'm going to write these little del things.
Okay. That's
Cool? All they are is soft d's. For me to remember, that's not the whole story here. There are more values.
okay.
Right? It's not the whole derivative, it's just part of it.
And you'll approach that another day.
Yeah, and when we actually do partial derivatives, we'll talk about that. For right now, you could think about it as the z slope, right? You guys all see that? Like, that's the slope on the z values. It's 1.
Okay, so the x, y, and z being 0 play like no part in this like at all?
No, not at all.
Okay.
So what does this mean? This means if I go 1 unit up, right, the temperature goes 1 unit up. Great. You guys cool with that?
So it's essentially the slope of the z coordinate at that point.
Yeah, it's exactly the slope of the z coordinate at this point. The slope of the z coordinate's the same everywhere, right? So the at this point part doesn't matter. You guys cool? Questions, Steels?
If the derivative had a z in it, would you plug?
Yes.
Okay.
If the derivative had x's, y's, or z's in it, I would plug these things into that.
All right.
You guys want to see an example? Just
Yes.
quick. Okay, so say I had a different function. I'm going to call this something else to avoid confusion. So I'm just going to say I've got another function that's g of x, y, and z is y, z. Cool? So what should gz be?
y.
Right? If I treat the other variables as constant and differentiate with respect to z, I should just get whatever the coefficient on z is, which is in this case 1. Okay, so if I wanted to take gz and evaluate it at 0, 0, 0, this notation's a little strange, right?
I think we've seen it
You guys have seen this notation on integrals, right? To evaluate it at. I want to clarify here that what I'm doing, right, is I'm taking a function gz and evaluating it at a point. Guys follow that? Another way to write that is to write gz 0, 0, 0, right? Which is literally just plugging 0, 0, 0 in for the x, y, and z. Cool? What do you get? Good, you get 0, right? What if I did gz at 1, 1, 1? I would get 1, right? You guys all see this?
Yep.
Cool. So this would be a case where it depends on something. Of course, you could make much more complicated things, right? And you guys are all capable of making horrible polynomials and multiple variables. Cool? Questions, Steels? This is glossing a little complexity, right? Because I'm like just giving you a way to calculate partial derivatives without telling you any of the subtlety. So don't get enamored with the idea that you can do the partial derivative section yet.
Okay.
Cool? All right. What were the other parts of this thing? I think there was a part C and a part D, but I lost the page I was on.
7.4.
So if you were standing at the point 0, 0, 0, in what direction should you move to increase your temperature the fastest?
Right. X.
So you guys are saying X?
Or no, negative y.
Oh,
The answer
Negative y, yeah.
Because it's negative 3 units every time we go forward.
Why did they have vectors? Okay, how about this? Just coarsely, without using material I haven't been to yet, which of the coefficient values is the biggest? Y is in terms of absolute value, right? But it's going, if I go in the y direction, right, what's the temperature doing? It's going down. So I want to go in the negative y direction coarsely at least, right? Yeah, I want to go in the negative y, the positive x, and the positive z kind of, right? You guys all see that? It turns out there's a way to figure out what the best direction is, but I'm not going to tell you that right now. Okay? So I would say do this. Make some reasonable guess about going back in the y, up in the x, and up in the z, all at the same time, weighted mostly towards back in the y.
How are you supposed to explain the answer like that?
Just like what I just did.
Just like to go with the X and the Y and Z.
Yeah, write that down. You guys don't have the tool to answer this in the best way possible. You could figure out where the isotherms are, right? These are planes, right? You guys all see that?
Yeah.
And if you were really clever, it might occur to you that if you have a plane
Use go in the direction.
and the plane is level temperature, right? That the best you can do is heading directly perpendicular off of that plane. Right? And there's a way to read what perpendicular to this is off of the equation for it. But you guys don't have chapter 13 yet, so you probably can't. If you're super clever, you might use, I don't know, some stuff about vectors you learned in physics, and this kind of an idea to stick that together, but man, that's a hard question. Cool. It turns out that you want to head in the direction of, well, 2 minus 3, 1, but whatever. All right, and then what's D say? D says if there's an isothermal surface, what is the isotherm? Where did their Z go?
It looks like they subtracted it to the other side and then made it.
Oh, yeah, gotcha. Okay, so they're telling me that something's an isotherm. So what's the isotherm? Yeah, that's a point where all this, or that's the points where the temperature is all the same, right? Okay, so they said that's when f of x and y is what? 2x minus 3y plus 17?
Negative 2x plus 3y.
Negative 2x plus 3y
Plus 17.
plus 17. Okay. So where the heck did they get this? Well, they took one of these, right? And they solved for z and got that. So I need to reverse engineer that process, right? You guys all see that?
Why did it go from 20 to 17 if they were just doing that? Well, that's something.
Because of this k.
Okay.
You guys see that? So I just might think, okay, well, z is minus 2x plus 3y plus 17. Okay, so I need to what? Yeah, let's see, I had a positive z, so I need the x's and the y's over with the z, right? Okay, so I'm going to subtract, add 2x and subtract 3y from both sides. So that's going to get me z plus 2x minus 3y is 17, right? And then what else do you need? Oh crap, you need a minus 20 on that side, right? Okay, so how do you get a minus 20 over there?
Subtract 37.
Wait, where do I want the minus 20?
On the left side.
Yeah, I want a minus 20 over here, right?
So just subtract 1.
So I just want to subtract 20. So if I subtract 20, I get z plus 2x minus 3y minus 20 is negative 3. And then you need to connect this piece here and that piece there, right? So that'll give you K is negative 3. So the temperature on that isotherm is negative 3 degrees Fahrenheit. Does that make sense? Cool. Questions, Steele? That question is fun because it lets us explore lots of things that we don't know yet. That question will be, remind me to ask that question again when we're done with gradients. And then it'll be really easy.